For today's math discussion, I'd like you to imagine a group of 100 prisoners who are all on death row. You may imagine this sad man as a representative of the doomed coalition. The director of the prison, being an absolute sicko, thinks of an interesting way to pass an afternoon, which also gives the death row inmates a chance at freedom. She tells them that they will each be ushered into a room, one by one. This room contains a cupboard with 100 drawers. Each drawer is numbered 1, 2, 3, and so on, all the way through 100. Each prisoner is assigned a number, 1 through 100, and those numbers, 1 through 100, are scattered among these 100 drawers in a random fashion. So, for example, the drawer number 1 may contain a paper which has the number 57, and the drawer labeled 2 may contain a paper that has the number 13, and so on. Each prisoner has an opportunity to open up to 50 drawers trying to find their number. If within 50 drawers a prisoner finds their number, all of the drawers are closed up again and the next prisoner comes to try to do the exact same thing. While the prisoners may discuss strategy beforehand, they may not communicate at all during this process. But if all 100 go through and achieve this task of finding their number within searching only 50 drawers, then all 100 of them are spared. On the other hand, if even a single prisoner fails to find their number by opening only 50 drawers, all of them will be promptly executed. The situation then, written out in meticulous, painstaking detail, looks like this, which you may want to pause and read through again if any of the details are unclear. Of course, the question in these dire circumstances is what's the best strategy for the prisoners to use to try to escape this hopeless situation? Of course, the most naive strategy would be to just play randomly, so each prisoner would enter the room and just randomly select 50 drawers to open, stopping when and if they find their number. So how successful would the random strategy be of just picking 50 drawers to open? If we let S1 denote the success of the first prisoner in finding their number, the probability of that success would just be 50 out of 100. They're randomly opening 50 out of the 100 drawers, so there's a 50 out of 100, or 1/2 chance, that they open the correct drawer, which contains their number. 50 out of 100, or 1/2, of course, doesn't seem like very bad odds, but you have to remember that for the prisoners to go free, all 100 of them would need to successfully find their number. In that case, if all prisoners employed this strategy, the probability that they all find their number, and thus are all pardoned and survive, would be this probability, 1/2, to the power of 100, because all 100 of the prisoners would need this probability 1/2 event to happen. Since they can't communicate during the process, and all of the drawers are closed up after each prisoner enters the room, the probability of each prisoner's success are independent, which is why we would multiply them all together. And if you know exponents, you know that this probability is vanishingly small. This is what it looks like as a percentage. The probability is 8 times 10 to the negative 31st power. Of course, the shocking part is going to be that with a little bit of math, we can devise a strategy for these prisoners to follow where their probability of success is actually going to be bigger than 30%. The central mathematical object in this problem is something called a permutation. The 100 prisoners, all having a number 1 through 100, have seen their 100 numbers permuted in some order by being scattered across these 100 drawers. It may help to briefly consider a smaller example. Suppose we only had 6 prisoners assigned the numbers 1 through 6. These numbers could then be permuted, or scattered among the 6 drawers, in many different ways. For example, the number 1 could be in the drawer labeled 4. The number 2 may be in the drawer labeled 3. The number 3 may be in the drawer labeled 6. The number 4 could be in the drawer labeled 5. Perhaps 5 is in the drawer labeled 2, and 6 then would be in the drawer labeled 1. There are two very important properties that make this a permutation of the numbers 1 through 6. First, each number is sent to exactly one position. For example, 4 is sent to position 5. It's not sent both to position 5 and position 2, it's only sent to one position, position 5. Just like 2 is only sent to position 3, and 3 is only sent to position 6. Each number is sent to exactly one position. The second important property is that the positions, which we see here written in green, represent the exact same numbers that we are ordering. So for example, 4 isn't sent to position 7, 7 isn't in the set of numbers that we are ordering. So when we permute the numbers 1 through 6, what we should see is exactly the numbers 1 through 6, just in some other order. Now, to introduce the genius strategy that's going to optimize the prisoner's probability of survival, let's consider a permutation with 8 prisoners. So if we have 8 prisoners, then here are our 8 drawers, and let's say that each prisoner can open 4 of these. Just like in the original problem, each prisoner could open 50 of the 100 drawers, so they can open up to half of all 8 drawers. Then the strategy that each prisoner will follow is simple. Let's say this is prisoner 1. Prisoner 1 should start by opening his numbered drawer, the drawer that is numbered 1. He should then view whatever number is inside the drawer as an instruction for which drawer to open next. If prisoner 1 follows this strategy, he will open drawer 1 and find the number 4. So then he will go to drawer 4. He'll open this up and find the number 3. Then he'll go to drawer 3, open that up, and find the number 5. Now he has one drawer left that he's allowed to open. That will be his 4th drawer, number 5, and there's his number, 1. So he succeeds, and it's up to the next prisoner. Of course, prisoner 1 was lucky to have that success. It's possible that this strategy fails, but this is just for demonstration purposes of the strategy. We'll of course get into the probability that it fails in a minute. As one more example, let's say prisoner 7 enters the room. He will follow the strategy and thus begin by opening drawer number 7, where he finds the number 6. So then he'll go to drawer number 6, open this up, and find the number 8. So then he'll go to drawer number 8, which has the number 2. So he has one more drawer left. He's going to open drawer 2, and bam, find his number 7, and he succeeds. Let's write out one more possible permutation of the numbers 1 through 8, and we'll start to see why this proposed strategy has the potential to be so effective. This permutation of the numbers 1 through 8 is similar to the one we just saw, though one interesting difference is that 8 is what we call a fixed point here. Drawer 8 actually contains the number 8. And that's totally fine. Remember, in the problem, the numbers 1 through 100 will just be randomly scattered among the drawers, so a situation like that may come up. Certainly, if prisoner 8 follows our proposed strategy, he will be in luck as he instantly finds his number. Now, there's much to be learned about this permutation by sketching it out with arrows. Here's the number 1, which this permutation is sending to the number 4. The permutation is sending the number 4 to the number 3. The permutation sends 3 to the number 5, and it sends the number 5 to the number 1. The permutation sends the number 2 to the number 7, and it sends 7 to the number 6. It also sends the number 6 to the number 2, and of course it sends 8 to itself. We thus see that the permutation is entirely composed of these cycles. We would call them disjoint cycles, because each cycle has no numbers in common. And in this permutation, if the prisoners follow our proposed strategy, they are guaranteed to all survive. Any prisoner whose number is in this cycle will only have to open the maximum allowed 4 drawers to get to their number. Prisoner 4 will go to drawer 3, then to drawer 5, then to drawer 1, where he will find his number. Any prisoner whose number is in this cycle will only have to open 3 drawers. For example, prisoner 2 will open drawer 2, then drawer 7, then drawer 6, where he will find the number 2. Any prisoner whose number is in this cycle will only have to open 3 drawers. For example, prisoner 2 will open drawer 2, then drawer 7, then drawer 6, where he will find the number 2. The fact that this permutation is made up of disjoint cycles is not unique. Ultimately, every permutation has to break down to disjoint cycles like this. Because this permutation has no cycle whose length is greater than 4, the strategy works and all prisoners survive. Of course, in general, this doesn't guarantee success because it is possible that a permutation contains a cycle of length greater than 4. Let's see one, for example. In this permutation, the number 3 is fixed, but the other 7 numbers make up a cycle of length 7. 1 goes to 8, which goes to 2, which goes to 4, which goes to 7, which goes to 6, which goes to 5, which finally returns to 1. So in this case, the prisoners would definitely die. And of course, back in the context of the original problem, with 100 prisoners and 100 drawers, it's not cycles of lengths greater than 4 we're worried about, but cycles of lengths greater than 50. The good news for the prisoners is that since 50 is half of all of the drawers, only one cycle could possibly have a length greater than 50 in any given permutation, so there aren't a ton of possible ways this could happen. But then, of course, the likelihood of this is the key question. If the prisoners apply this strategy, what is the likelihood that they survive? We know that if the permutation of the numbers among the drawers doesn't have a cycle of length greater than 50, they're guaranteed to survive. Otherwise, they're guaranteed to die. So the survival probability is simply the probability that a random permutation of the numbers 1 through 100 does not have a cycle with a length greater than 50. And to calculate this probability, we're going to begin by counting how many permutations there are that do have a cycle with a length L greater than 50, and that's pretty straightforward. If we have a permutation of the numbers 1 through 100, and that permutation has a cycle of length L, well, there are 100 minus L other numbers in the permutation that aren't in that cycle, and those numbers could be ordered in 100 minus L factorial ways. Remember that the factorial is the product of this number with all positive integers less than it. So that's how many ways the 100 minus L numbers not in the cycle could be arranged. As for the L numbers that are in the cycle, we must first take the number of ways we could pick those L numbers that are in the cycle, which is 100 choose L. This counts what are called combinations. It's called a binomial coefficient, and the formula for it, in case you've forgotten, is 100 factorial divided by L factorial times 100 minus L factorial. So this is the number of ways we could pick L numbers from the 100 numbers to be in the cycle. Now, for those L numbers that are in the cycle, how many different ways could we order them? You might want to say that would be L factorial. There are L numbers in the cycle, and they can be ordered in L factorial ways. However, because they're in a cycle, counting them that way would not be quite right. For example, consider this cycle of 4 numbers. I could start this cycle with 1, or 4, or 3, or 5, and still have essentially the same exact cycle that goes through the same numbers in the same order. Because of the circular shape of a cycle, the first number is kind of meaningless, and so it's not L factorial, which counts the number of ways we could order the L numbers in the cycle, but rather L minus 1 factorial. Once the first number in the cycle is selected, the L-1 numbers that could be chosen next, those are all L-1 meaningfully different possibilities. But the first number, we basically have to exclude that when counting our choices. So this is the number of permutations of the numbers 1 through 100 that contains a cycle of length L. We'll then want to do some simplifying and find that this comes down to a very simple expression. We have on the left 100 minus L factorial. Then, remembering what this binomial coefficient is equal to, we have 100 factorial divided by L factorial times 100 minus L factorial. And then, of course, on the right, this is getting multiplied by that L minus 1 factorial. We then see some cancellation. 100 minus L factorial cancels out with 100 minus L factorial. And L minus 1 factorial divided by L factorial is just going to leave a single factor of L in the denominator. And of course, 100 factorial stands strong in the numerator, leaving us with a simplified expression of 100 factorial divided by L. Again, this is the number of permutations that have a cycle of length L. So how many permutations have a cycle of length 51? Because, for example, that would be one of the possibilities that would guarantee the prisoners die. Well, from our formula, that would be 100 factorial divided by 51. If a permutation has a cycle of length 51, then any prisoner whose number is in that cycle would have to open 51 drawers to find their number, thus none of them would exceed because they can only open 50 drawers. Of course, that's not the only cycle length which would present a problem. Any longer cycles would also be prohibitive. 100 factorial divided by 52 would be the number of permutations with a cycle of length 52, and any permutation like that would also certainly lead to the prisoner's demise. We have to continue adding up all of these numbers of permutations with cycles of different lengths, all the way up to the maximum possible 100 factorial divided by 100 for the permutations that have cycles of length 100. And remember, the fact we're starting with just over half of 100, so 51, that is significant here because we know that none of these terms are counting the same permutations. If a permutation has a cycle of length 51, it can't possibly have a cycle of length 52, 53, or anything else, because 51 is more than half of 100. And of course, the same applies to all of these other cycle lengths. So this here is the total number of permutations that contain a cycle of length 51 or greater. These are counting exactly the permutations that would doom our prisoners. Now, what's the probability that a random permutation of the numbers 1 through 100 actually is one of these permutations? Well, we would just have to take this number and divide it by the total number of permutations of 1 through 100. That is just 100 factorial. So we divide by 100 factorial. Again, 100 factorial is the number of permutations of 1 through 100. This then, the probability that a random permutation has one of these prohibitively long cycles, after cancellation, 100 factorial is going to cancel out with all of those 100 factorials in the numerator. This probability ends up being 1 over 51 plus 1 over 52, and so on all the way up to 1 over 100. Remember that dividing this by 100 factorial causes all of those guys to cancel out because of the distributive property. Now, to help finish our work here, some notation will be helpful. There is a nice symbol for the sum of the reciprocals of numbers, 1 plus 1/2 plus 1/3, and so on, all the way up to plus 1 over 100. This is called the 100th harmonic number and is denoted H100. Similarly, the sum of reciprocals 1 plus 1/2 plus 1/3 and so on, all the way up to plus 1 over 50. This is the 50th harmonic number, denoted H50. So then we could write this, which again is the probability that a random permutation contains one of these long cycles. We could rewrite this as H100 minus H50. 50, because it has the sum of all of those reciprocals up through 1 over 100, except for the first 50, which is why we're subtracting h50. Then finally, we arrive at our answer. What's the probability that the prisoners will survive if they use our proposed strategy? The probability is 1, which we view as counting 100% of all permutations, and then subtract the permutations which will result in disaster. The percent of permutations for which our strategy will fail is exactly this number that we just went over, h100 minus h50. So from the 100% of all permutations, this is taking out the portion of those permutations which have prohibitively long cycles that would result in our strategy's failure. Now, the harmonic numbers can actually be well approximated by natural logarithms, and so we could easily approximate this on a calculator as 1 minus the natural log of 100 minus the natural log of 50. And this is where we then finally arrive at that frankly stunning survival probability of 0.30685. Or if we compute this more directly without a natural log approximation, we find the probability is about 0.31183. So you can see the natural log approximation is pretty good, but definitely off by a little bit. So thus, we've demonstrated there is a solution to this problem which is surprisingly effective. At the outset, the situation seemed pretty much hopeless for the prisoners. We saw that applying a naive strategy had a probability of success that was pretty much just 0. But by simply opening your numbered drawer and viewing the contents as instructions for which drawer to go to next, from the nature of permutations and cycles, the likelihood of the prisoners all finding their number is pretty significant. It is perhaps even more impressive that this strategy does indeed turn out to be the optimal strategy to the problem, which was proven in 2006 by Curtin and Warschauer. So if you ever find yourself in this situation, not only is this strategy good, but you can rest easy knowing that it is in fact the best. Let me know in the comments if you have any questions, and be sure to subscribe for more of the swankiest math videos on the internet.
From my fate, twisting to escape this. Climbing out of my wrist if you can break it. Breaking in my past, I'm making it up fast. So slow down, give me the time so I can fake it. Erase the tune of words and just how I say shit. And let me speak my poetry to your face. It's not intimate if you ain't listening. Not infinite if you ain't really into